Yeah, right here for the microphone. All right. Welcome, everybody. So I want to start off by saying that these seminars are planned well in advance and without knowledge of the SEC football schedule. So any correlation with the Tennessee schedule is purely coincidental. Yeah. So, it's my pleasure to introduce Professor Lisa McElwee-White. She obtained her PhD from Caltech, and after a postdoctoral stint at Stanford, she stayed on and became an assistant professor there. And then she moved on to the University of Florida in '93 as an associate professor. And there she has built a very successful research program based on organometallic chemistry and applications for catalysis and also material science. And she's garnered a number of awards for her contributions in this regard. She was recently the recipient of the 2015 Florida Award, and she's also a Charles Stone Award recipient, and she's also an ACS Fellow. Her group now is focused on the design and synthesis of organometallic complexes for different deposition techniques, and Lisa will tell us a little bit more about that today.
Thank you very much. Well, thank you for the invitation. It's always nice to know that your former students grow up and become academic adults and get jobs and do things and are wonderful. So I'm going to tell you a couple of interesting stories today that are along the themes of what happens when someone who's really a physical organic chemist gets drawn into the world of inorganic materials problems. So my training is really classical physical organic chemistry. I did high-spin organics as a graduate student. I postdoced in a lab that did organometallic reactions. Okay? And so I got drawn into these applications because there are places in the world, in the scientific world, where chemistry can be tremendously useful, but these are bits of the ecosystem that are not occupied by synthetic chemists. They're occupied by chemical engineers, material scientists, physicists. All of these people are fabulous, but they have a different skill set than we have. And so sometimes when you step into something entirely different, you can end up in some really interesting places. Okay. Oh, good, this is working. I made the bold and daring move of upgrading to Windows 10 right before I came here. And I had no idea if the Windows 10 drivers actually worked with projectors. So if my computer turns into a flame ball in the middle, you'll know what happened here. So anyway, this is where we got our start into the materials business. So what you see here is the cartoon of a contact structure in an integrated circuit. So at the bottom is the silicon wafer, the semiconductor that's the heart of the chip. This part that says copper is the wiring of the chip, that's the metallization. These are dielectric layers, they're insulator layers. And you see everywhere there's copper in this cartoon, there is a black line drawn. And that black line is diffusion barrier material. That's a thin layer of something that prevents the copper from migrating throughout the chip and shorting it out. Okay? And so at the time that we got into this, the industry was just making a transition from aluminum metallization here to copper metallized chips. And that was causing a giant kerfluffle because copper migrates through the old titanium nitride barriers that were used with aluminum-based chips. And so along with that was the problem of feature sizes on the chip getting smaller and smaller and smaller. So the layers are getting thinner, the demands of aspect ratios are getting more stringent. And so they needed to figure out not only a way to put something in here and not block up the whole feature, but also figure out what material would block copper diffusion. And so at the time, tungsten nitride and the tungsten nitride carbide ternary material were basically one of the best candidates for the switch to copper metallization. They're going to use those as diffusion barrier material. Okay. And so the technology that was used then and is still used now is physical vapor deposition or sputtering. But there's a problem with sputtering. And that problem has to do with conformal coverage of features on a chip. There's all these little tiny features. And this is a cartoon of what goes wrong with sputtering. This is greatly exaggerated, okay? But sputtered material comes in line of sight. So wherever it hits, it lands, and there it is, right? And so if you think about sputtering material from the top, you're going to get thick coverage on the top of the feature. The side wall is not going to be covered well. You kind of block it. This is called a pinch-off site. And there are going to be holes down the side wall. And in fact, this is an SEM image, not ours, of sputtered material on a high aspect ratio feature. You can see this light gray stuff is the sputtered material. So it's thick here, and it's not very well covered down the sidewalls. Now, if you think about putting your material down with a chemical reaction, synthesizing it in place, as it were, then you don't have this problem, because the reaction kinetics for materials deposition are the same on the top as they are on the sidewall as they are on the bottom. And so you can get a much better approximation of perfection. So this is a profile of material deposited by what's called chemical vapor deposition. And so then when you fill this feature with copper, with the problem here, we've got pinch off, we have a void, we have stuff leaking out the bottom, and then this is a much better solution to the problem. So here's chemical vapor deposition. I know some of you here are very, very familiar with this process. You guys forgive me while I explain the rest of it. So chemical vapor deposition brings in reactants in the gas phase to a heated substrate. So this would be your silicon wafer here. The heat comes in from the bottom. You heat this up to whatever temperature you need to run your chemical reaction. And then your material is synthesized in place here. And then gaseous byproducts get pumped out in the reactor effluent. And so this is the chemical vapor deposition process. And so now we're introducing reaction chemistry. Right? For sputtering, you take a target of whatever it is you're trying to lay down, you hit it with ions, and stuff sprays out. With CVD, you have to design reaction chemistry. And so this is where chemists and their ability to look at mechanism and synthesis start becoming valuable. So this happens to be the reactor that belongs to our collaborator, Tim Anderson, in chemical engineering. This is an aerosol-assisted CVD reactor. So we actually give them the precursor in solution. It's syringe pumped into this nebulizer. That's a cartoon of the nebulizer. Hits a vibrating quartz plate, sprays up as aerosol, is transported in partial vacuum through this impinging jet, gets sprayed out through a shower head. The silicon wafer sits here. The susceptor is the heating element. The reaction is there, okay? And then the byproducts get pumped out. And of course, because this is an engineering slide, it says to vacuum pump, like we're going to pitch it. What we care about is that also it goes to a mass spectrometer out here. So we can look at the fragments of what's coming off and use that to back out some of the reactivity. So that's the reactor. Okay, well, what about the chemistry? Well, whenever I talk to a collaborator about a deposition problem, I ask them a few questions about what's important about the chemistry we're going to do here. So if we're talking about nitride diffusion barriers, the decomposition mechanism under those conditions, it's thermal, right? We're heating the wafer from the bottom, okay? The deposition temperature, oh, for you organometallic chemists, low temperature CVD is 400 C, okay? So I have actually had my industrial and engineering collaborators ask me with a perfectly straight face, can you think of an organometallic molecule that will decompose at 400 C? Got it, okay. However, for reasons which have to do with the processing of chips, lower is better. So you want to minimize the temperature. You need to be able to control the stoichiometry of the films for materials reasons. And interestingly enough, for this particular problem, You want to grow amorphous material. And that's because for diffusion barriers, if you have polycrystalline material, the mechanism for failure is migration of copper along the grain boundaries. And so if you have crystallites, you want to have amorphous stuff in between them because it stuffs the boundaries and blocks copper diffusion. So you really want to grow amorphous stuff. And that means that if you have carbon depositing in your material, for this particular application, that's a plus. If you want to deposit from organometallics, people always say, you're going to get carbon in your stuff. Well, if you pick your problem carefully so that that carbon is an advantage, you're going to win. Okay. So the carbon's fine. All right. So what was done before us? So at the time we started looking at this problem, which by now is about 10, 12 years ago, this was the state of the art in depositing tungsten nitride. Okay. This is a classic example of chemistry designed by engineers. Is anybody out here an engineer? Am I insulting anybody? Well, you deserve it. No, I'm just kidding. We'll talk later about engineering designed by chemists. That's not really very good either. Okay, so you can see how this process works, right? So we're talking about chemical vapor deposition, and everything's a transport problem. Question 1, is it volatile? Check. Question 2, can I buy this in a rail car because I'm not going to synthesize anything? Check, commercially available. Oh yeah, does it have the right elements in it? Check. We got a winner, let's try it, okay? Since most of the people in this room are chemists, we have a different thought process for how to do this. For example, we balance equations in our head, okay? So tungsten nitride, yeah. What is this thing that I've listed as byproducts for that top reaction? Students? HF, 6 equivalents of HF. And the bottom layer on diffusion barrier deposition is a silicon wafer. Anybody see a problem here? All right, okay, good. All right. So this is a place where someone who's got a chemistry background can come in and start making a contribution. So you ask me, how should I lay down tungsten nitride on silicon? And the answer is not going to be tungsten hexafluoride plus ammonia, okay? So let's take a look at something a little different. So this is our first generation of designs here, and this is a chemist looks at the same problem, okay? So if you want to lay down a film that's primarily tungsten nitride, let's start out with a molecule for which a tungsten nitrogen bond is pre-existing, so we know something about stoichiometry, and it's the strongest bond in the molecule. Okay, so here's an amido compound. In this particular drawing of it, it's drawn as a triple bond. It is linear, for those of you who are aficionados. Okay, that's a very strong trans effect ligand, so my acetonitrile is going to be labile, trans to it. I can run H2 in my carrier gas, and I can remove these 4 chlorides as HCl. HCl is better for the silicon wafer than HF. It's a problem with process equipment, and we're going to come back to that. Okay, I'll get rid of it by the end of the talk. And then all I have to do is break 1 nitrogen-carbon bond, and I have a building block for tungsten nitride thin films. Looks good, right? Okay. Let's check it out. And here's where my group starts doing mechanistic chemistry. Before I ever give a precursor to a collaborator, I do as much pre-screening as I can. Okay? So we do as much mechanistic work, ask ourselves, what is the decomposition of this going to be like? And so here's this molecule that I just showed you. And these are NMR kinetics for loss of acetonitrile. And I know I'm looking, well, actually it's acetonitrile exchange, okay. But it's dissociative exchange because delta S double dagger is positive. So I'm good. So I'm looking at acetonitrile loss. And if you're good at converting 1/T to T in your head, this reaction is fairly fast between 50 and 80 C, just a little above room temperature. So I'm good for losing my trans acetonitrile. Okay, so now we could actually probe the ability to break the CN bond, here's our original molecule, by mass spec. Now, if you're going to tell me that mass spec is gas phase ion chemistry and my CVD process is neutrals, I know that, okay? But it turns out that this actually works better than we deserve, and that the weak points for scission of the molecule are pretty much the same as the ones in the ion. Okay? So what I'm looking at here is I'm changing the R group, this R group on the nitrogen, that mini nitrogen you can barely see, from phenyl to isopropyl to allyl. So what I'm doing, physical organic chemists, is I'm varying the bond dissociation energy of that CN bond. That, remember, all I have to do is break a CN bond to get my building block. And I'm looking at the amount of terminal nitride versus intact imido ligand there. And so where the bond association energy is high, this is nitrogen to aryl, what I see is not much cleavage. Almost all my base peak here is the intact phenyl imido. I get 4% cleavage. With the isopropyl, where I now have secondary alkyl to nitrogen from my bond cleavage, all of a sudden, the terminal nitride is the base peak, and I see about 42% bond that's still there. And then allyl, where I've weakened that bond another 15 kcals per mole, the base peak is still the terminal nitride, but I see only 5% of the intact allyl amido. So I know that at least under the gas phase ion conditions, I can break that bond I need to break to do the deposition. Okay, so try the experiment. What do we get? At low temperatures, yeah, it still kills me to call 450C low temperature. But at low temperature depositions, my material is X-ray amorphous. I don't see anything in the XRD. As I grow at higher and higher temperatures, I start to see crystallization. And these peaks are going to allow us to identify the nature of the crystalline material. Okay? And here's the temperature equals 700. Here are the standards for tungsten nitride and tungsten carbide. I am still worried about the carbon, right? So I check these. You'll notice that these XRD patterns look very similar, and that's because the majority of the diffraction is off the tungsten atoms, and you have the same tungsten lattice here for both of these. The sublattice is occupied here by carbon, here by nitrogen, and what we grow is somewhere in the middle. It's the ternary phase, okay? So we have our sublattice occupied by some nitrogen, some carbons, and some vacancies. Well, at this point, we'd identified the material, at least the crystalline bits, and it wasn't quite tungsten nitride, but right about that time, somebody published a paper on how fabulous a barrier material the ternary nitride carbide phase was. Fabulous. We win. We're going with it. Guess what? All this time, we really wanted to grow that ternary phase because that's such a great barrier material. Isn't that how your research works? Yeah. All right. So that's what we're growing. That's the crystalline part. For a bulk measurement, you can do XPS and look at this. What we see is that there are two different types of tungsten. One of them corresponds to tungsten oxide. This is from post-growth handling of the samples in the moist Florida air. If you've ever been in Gainesville, Florida in the summer, it's about 95 degrees and 95% humidity. So when you take the samples out before you can get to the XPS, you have an oxide layer. And in fact, you can depth profile from the top of the sample to the bottom, and you watch the oxide content go down as you sputter down. So it's all coming in from the top post-growth. Okay, so here's our carbon. There's carbon in the lattice, that's this. There's carbon that's amorphous, blocking the grain boundaries. The nitrogen is all in the lattice. So we know what we've got. So let's do chemistry. So this is now a plot of the energy of activation for film growth versus the CN bond association energy. We run film growth kinetics by doing cross-sectional SEM. So we determine the film thickness in the cross-section and then work out growth kinetics from there. And you can do this at different temperatures, and you can do Eyring plots, and you can back out activation energies just like you do in any other kinetics. And take a look at this. The activation energy for film growth plotted against the CN bond association energy, that's linear. There's your rate determining step for film growth, is cleavage of that CN bond. Okay? Now, you remember that my low temperature growth there was 450, and that's really too high. I'd like to take it down. So I can drop the activation energy for film growth by changing the bond association energy of that bond. Okay, so how do I do that? Well, let's go from N carbon to NN, because a nitrogen-nitrogen bond in a hydrazine is about 20 kcals less than a CN bond in an amine. So what I've done is I've knocked back off my activation energy for that cleavage. And there's some other advantages here, but let's just talk about temperature for a while. So this is exactly the same molecule as that one, but this is now a dimethylamide group. So this is the hydroxido compound instead of the amido. And take a look at this. These are film growth results. These are nitrogen contents of the films from Auger Spectre, but that doesn't matter. What I want you to look at is the lowest temperature at which I could get decent film. So this red one, we won't call this orange and blue because I realize, you know, orange and blue is bad colors for you this week. We're not going to do that. Okay. So this line is now red. All right. So the red line for the isopropyl stops at 450. That's the lowest temperature where we could get good film. Here's the hydroxido, and I'm growing film out at 300. Aha, okay. And not only that, I can manipulate the nitrogen content, and there are reasons why you'd want to do that. So that's cool. So now, let's talk mechanism for another minute. So my collaborators have a second really cool, their reactors are cooler than ours. We have a CVD reactor in my lab, but it doesn't do this. So Tim Anderson's group has one with quartz walls and a laser that goes through to a Raman spectrometer behind it. Okay. So this reactor is a little upside down from the other one. The precursor's spraying in from the bottom. The silicon substrate is clamped here, and there's a translation stage to bring this up and down. So your heat is here, the laser beam is there. If you think about the temperature gradient that comes from the heater, by moving this up and down and keeping the laser position constant, you can temperature profile the gas phase species inside the reactor while you're growing film by taking the Raman spectrum, what's in the middle. Okay, and this is really cool because if you think about CVD, you have a heated surface here, you're growing at the surface, but there's a temperature gradient that starts, say, from 400 here going on up. And so part of your CVD chemistry always takes place in the gas phase because the molecule is being heated as it approaches. So it's a mixture of gas phase chemistry and gas surface chemistry. And so this reactor allows us to look in situ at the gas phase part of the chemistry during the reaction. And what do we see? Well, if you look at that hydroxido compound, we see a bunch of things. We're spraying from benzonitrile, so we see nitrile exchange. So this compound we see, and we can make authentic samples of that. We see another vibrational mode at 1189, which by DFT calculations is a vibrational mode of the hydroxido, the unsaturated one, so that's minus the acetonitrile. And then we see the coolest thing ever, which is these two compounds. So if you go back to what I said when I was talking about bond dissociation energies, I said the rate determining step is cleavage of that bond. But it tracks linearly with the bond dissociation energy, and bond dissociation energies are homolytic. For that plot to work, that has to be a radical cleavage, okay? And so if we're doing exactly the same thing here, it's another homolytic cleavage, I should make dimethylamminyl radical and that, a nitrogen-centered radical here. These two compounds, which we see in the Raman in the gas phase, are dimethylamine and the imine. These are the disproportionation products of dimethylamminyl radical. Okay. And this peak at 3426 is when that radical abstracts a methyl from this, or abstracts a hydrogen from the methyl here. That gives you another equivalent of that and one of these. So we're seeing experimental evidence for that homolytic pathway that we had proposed. And by the way, you can do this with the isopropyl compound, and you see propene. Exactly the same. The isopropyl stuff isn't published yet. We're writing it up now. So this all works. All right. So now if I really want to drop my temperature, my rate determining step is still cleavage of this bond. Let's just get rid of the bond. What if you make something like this? Well, not that one, because it's a radical, right? And I can't make that and have it be stable. What about something like this? Okay? So now we're going to go from NC bond to NN bond to N not bond. And so we've gotten rid of the old rate determining step, which is going to shift the rate determining step somewhere else. Okay, so how about this molecule? Well, that molecule was actually made by Kit Cummins' group in about 2000, and they never published it because their synthesis was horrible. I didn't say horrible. Their synthesis was suboptimal. So it's buried in someone's dissertation that I got a copy of from Kit. He's horrified now that the molecule is actually worth something. Okay, so that molecule looked really interesting. My students figured out how to make it in 3 steps from commercially available material. Okay. So we start from tungsten hexachloride and TMS azide, and that gives, this is a tetramer of the terminal nitride with 3 chlorides. And this chemistry had been done by the Denneke group in Germany a long time ago. The part that was brilliant on the part of my students was they figured out how to break up this tetramer with t-butoxide, which brings you to this compound, okay? And then we join the Cummins synthesis here and take that compound and transaminate, and that gives you this compound. And if you want more of these, you can continue the transamination process. Because dimethylamine is volatile, you take any other secondary amine, put it in there, you get transamination, blow off dimethylamine, and we can make all kinds of these. We made about 24 of them now, including the really hindered tris diisopropyl one, which is, has to be done a little different way, but we can get hold of all of these. And so then we did depositions, okay? And it turns out that you can take this one, this is the methyl one, and you can deposit nanoparticles at low temperatures. And at slightly higher temperatures, you can deposit films. This is a high resolution TEM of a 5 nanometer film that passes the diffusion barrier test. And we do this at low temperatures, except we've entirely rewritten the book on what low temperature means. 400? I don't think so. 75 for the nanoparticles, and 125 degrees C, we can grow films that pass the diffusion barrier test, okay? And so that means that we've taken the CVD of these materials from the realm about where you have to think, oh, we can do this on silicon, we can do it on glass. At 125, we could do this on organic electronics. You know, we could do it on polymers, all kinds of things, because we've been able to drop the temperature down into a range that's just unheard of for this kind of chemistry. And so how do you do diffusion barrier tests? Well, here's one of the ways. So we take the silicon substrate, we grow the material on there, we can put copper on the top either by CVD or by sputtering. You heat that to 500 C for 30 minutes, and then you start peeling off the layers. So we remove the copper with nitric acid, so it's just barrier and silicon. Then we dissolve off the barrier with basic peroxide, and then you treat it with dichromate and HF. And if copper has diffused through the barrier, it's made copper silicide. And the copper silicide is etched away by this reagent. And so if your barrier fails, you get something that looks like this, where these little white lines are what are called etch pits from etching out copper silicide. And so, but that's not our barrier. That's one that didn't work, okay? So C is what happens as deposited with no annealing. This is our barrier. And A and B are our barriers tested under these conditions. No etch pits, even at high magnification. So these barriers actually do pass the diffusion barrier test. So to sum up the CVD part, this is what we were able to do by doing some mechanistic chemistry, right? Before we got really started on this, everybody was stuck at 400 degrees. And that's because all of these precursors had intact amido ligands. There's N-T-butyl, N-T-butyl, here's our N-isopropyl, N-T-butyl, and the rate determining step is cleavage of that CN bond. And so as soon as you step away from that as a design feature, then here's the hydroxido, the drops to 300, and get rid of that bond entirely, and now depositing at 125. And so that's what happens when mechanistic chemists get involved in these kind of projects. Okay. So what else can we do? Once people found out that we could do this in my group, people started approaching me with, I don't want to call it weird stuff, say much less common approaches for precursors. Okay. And so here's another technique. This is surface plasmon mediated chemical solution deposition. Okay. This is being developed by my junior colleague David Way at Florida. And so David came to me with this idea. He said, I want to grow nanostructures on nanostructures for reasons which you'll see at the end. He said, we can make these substrates. These are silica balls, and they have silver sputtered onto the top of them. These are nanoscale things. They give a really strong surface plasmon resonance response, and I would like to use that as a driving force to grow material. And because I'm a physical organic chemist, I said, what's surface plasmon resonance? Okay, that's where a lot of my projects start, like, what's that? Okay, so For those of you who know, I apologize for this discussion. For those of you who don't know, here's the organic chemist's explanation of this. So if you have a metal nanostructure, these have an optical response. So you're irradiating these, in the case of our balls, with visible light. It's like 500 nanometers. What happens is you get a field or a wash of electrons back and forth in response to the electric field, because this is large with respect to the nanoparticle. Okay, and so it's basically it's a sort of excited state. And what happens is this will eventually relax, as all excited states do. And one of the things that it does is give off heat. Okay, so you end up doing heating of nanoparticles, making hotspots on nanoparticles with visible light. Okay. And so my students made this animated slide. They said, you have to take this slide. All right, so here's the experiment. So here's our precursor. It's in solution. There are the little silica spheres that are coated with silver, the nanostructured silver substrate. Okay. So we take light, and then the response is that these heat up, so these are hot spots, okay? And the precursor comes in, and it decomposes on the hot spots and leaves gold nanoparticles behind. And then we have byproducts. If they're not volatile, they stay in the solution. If they are, they come out into the gas phase. And so this is a fun precursor design project. It's fun because, first of all, it's all being done in solution, so we don't have to worry about volatility. And that's the bugaboo on CVD precursors. But, so how do you do this? Okay, so here's the setup. It's very simple. This is physical chemistry even an organic chemist could love. This is literally a beaker full of benzene inside a foil-covered box. Okay, this is a xenon arc lamp with a 515 nanometer long-pass filter, and this is the experiment in progress. The hard part is making the nanostructured substrate. Okay, this part is easy. All right. So I went through my same checklist of questions with David, like what am I supposed to be looking at here? I have no idea. Okay. So the decomposition mechanism of the precursor, honestly, we haven't got a clue. It could be thermal because we're generating hot spots. It could also be electron transfer because we have excited state electrons. It could be the tremendously high electric fields that are generated and associated with surface plasmon resonance. We haven't got a clue. But because I know how to deal with thermal, we're going to assume thermal for a minute. Okay, deposition temperature. Well, the decomposition temperature of the precursor has to be lower than the hotspot temperature. What is that? We'll come back to that in a minute. Optical properties, we want the compound not to absorb where the substrate is because it will be competing with light. Nope, nope, nope. And we'd like to be making pure metal because the whole idea is nanoelectronics eventually. And so then we come to how do you figure out what the temperature of the substrate surface is? Right. So we're talking about little bitty hotspots on little bitty nanoparticles. It's not a thermometer problem. It's not a thermocouple problem. So the answer turns out to be we're going to bracket it with chemical reactions that have known onset temperatures. So because people have cared about food oils for a long time and what temperature they start decomposing, these are like ag problems. It turns out that there is a known set of food oils that have onset temperatures for decomposition, and those temperatures are known. So you can bracket it by looking for polymerization. So if you paint your substrate with soybean oil, I mean really soybean oil, right? Okay. And you irradiate it, and you take a Raman spectrum before or after. If you think about polymerization of double bonds, you're trading vinyl CH bonds for aliphatic ones, and you can distinguish those in the vibrational spectra. So here we have vinyl CH, aliphatic CH, and the ratio changes after irradiation, and soybean oil begins to polymerize at 230 C. So the answer is the hotspots are at least 230 C. So now I have a temperature range to work with. And so this is the TGA, the thermogravimetric analysis of this particular compound, methyl gold triphenylphosphine. Okay? And so what I'm doing is I'm following the mass of the sample versus temperature. This plunges around here. This is 230 degrees C. This is my barrier. Okay? And the residual mass after this decomposition corresponds to metallic gold. So I have a precursor that decomposes to metallic gold below the hotspot temperature. Okay, optical properties, well, 515 nanometers is the long pass filter. There's the UV spectrum of my compound. It looks like the UV spectrum of benzene because what I'm seeing is pi to pi star in the phenyl groups of the phosphine. And this is the extinction spectrum of the substrate. So this is absorption plus scattering. So here's where the long pass filter cuts off. So the lambda max for this is somewhere around, I don't know, 600 to 700. So we have lots of optical range where we can irradiate the substrate, but not the precursor. And what happens? This actually works, kind of to my utter amazement. So before deposition, this is an SEM image of the substrate. Okay, it looks like little cauliflowers. After the deposition, it looks like little cauliflowers with white spots. Those spots are gold nanoparticles. Okay, we can characterize those. Okay, here's the XPS. We can see the precursor XPS is gold 1. The nanoparticles are gold 0. Okay, there it is in the EDX spectrum. Now, what's really cool about these is whenever you make nanoparticles and you make them in solution, you have to control the aggregation. And it's controlled by surfactants or it's controlled by halide ions. And so when you make colloidal gold in solution, its surface is covered with stuff. And if you want to use those nanoparticles for catalysis, for SIRS, for anything, you've got to get the stuff off of them or wait for it to dissociate. These nanoparticles are clean. What could be on them? Phosphine? Nope. So this is the XPS phosphorus region of what the precursor looks like. That's the gold nanoparticles. The phosphine all ended up in the benzene solution. Okay? What happened to the methyl groups? Eventually reductive elimination to form ethane off the gold nanoparticles. And so we can make size-controlled gold nanoparticles with absolutely clean surfaces. And by the way, they're great at SIRS. That's in the paper if you care. But it's a cool way of doing synthesis. Okay, so what's going on? Well, we decided to look at this computationally. This is a collaboration with Charles Musgrave at Colorado. And the first obvious thing is, well, the precursor absorbs onto the surface and decomposes. So here, computationally, is absorption of the precursor onto the surface. It's about 38 kcals downhill. And so then you calculate that you lose the phosphine, okay, you end up with gold methyl, there it is, okay. This all looks like reasonable activation energies. And so if you look at this whole surface, here's the precursor absorption, there's what you just saw on the other slide, here's the reductive elimination of ethane. And you look at that, what you see computationally, you think, wow, that ought to be just so spontaneously really fast at room temperature without any light. I mean, this thing ought to be going on the silver surface. And then you do the control experiments. Here's the substrate. Here's the substrate held 3 hours in the dark. There's no deposition. Okay? Then here's the substrate irradiated. There's the gold nanoparticles. They're there. And so clearly that reaction surface can't be right. It just doesn't match what we see experimentally. So what did we do wrong? And the answer is we've got a solution reaction and we did a gas phase calculation. You know, molecules coming in from the gas phase onto a naked surface. What we have in a benzene solution is a little different because we have a silver surface and benzene absorbs onto silver, right? Okay, so now let's look at here's our surface, there's the benzene, and so each benzene is 14 kcals downhill, absorbing, and it takes up a surface area of 16 square angstroms. Here's the precursor absorbing. It takes up 45 square angstroms. So if we start here and we get there, we need to remove 3 benzenes from the surface. You do the math, and you discover that it's 4.5 kcals uphill to absorb the benzene onto, or to desorb the benzene and absorb the precursor. So that's not what's going on here. And so, but if you look at methyl gold fragments, they'll fit in between the benzene. So you can put methyl gold down without having to desorb benzene. So now we start looking at solvent control for all of this, because if you try to bring this in and displace 3 benzenes for it to have room, that doesn't happen because it's uphill. Instead, what we have is dissociation of the phosphine in solution. This is a reaction that Jay Kochi studied very well in the 1980s. And now we have methyl gold fragments, and we absorb those onto there. Okay, so we have these, they're tucked in between. And then here's a reaction surface for one of them. Here they are migrating together to make a dimer. Then you see migration of the methyl from one gold to another. This is still up only 13 kcals. And then the reductive elimination of ethane, which is what we see experimentally, is downhill. And so this is one where we had to do some computational work to figure out what was going on in that particular case. Okay, so why would you want to do this? It's cool as a deposition method, but spheres aren't very interesting. These are more interesting. This is a substrate covered with silver bow ties that David Wei's group made with electron beam lithography. And this is a single bow tie, okay? And so now, when you start looking at the surface plasmon resonance, what you see is that if you calculate where the RF field should be, and I have to thank George Schatz at Northwestern for doing this calculation, it should be concentrated in between in the middle. And so now, if you can get the deposition to follow where the EM field is, you have a way of soldering that bow tie together. And if you look at different shapes and do this calculation over and over again, you can see how you can control the SPR response to be at different places on the shapes. And so the idea behind this project was to use this for soldering together components for nanoelectronics and control the deposition site by how the light works. Okay. And so now do the experiment. I'm showing you one bow tie. I'm not showing you like 7,000 of them. But look at this. So this is afterwards. See that and see this. Those two are little gold nanoparticles grown on a silver bow tie by irradiating with this polarization where it should be right there. And that's really kind of cool, okay? And if you don't believe that, here's the NanoSIMS profile of gold after deposition, and there's the intensity of the gold. You can see the bow tie there as a shadow after the deposition. So we have at least the initial hints that we might be able to do directional growth in this way, which is cool. Okay. All right, last story. This one's a quick story. This is electron beam induced deposition of metal nanostructures. So this was another one of those cases where somebody came to me and said, you can make precursors, can you do this? Okay, well, we'll try this. What is this? Well, this is a gas doser tube with an organometallic precursor. This is an electron beam, okay? And this is a structure that's growing up as the electron flux causes decomposition of the organometallic precursor. And the reason why this is interesting is you can basically do, it's kind of like 3D printing of metal nanostructures, because if you use an SEM tip as your electron source, you have 3D control of where the tip is, and you can basically just draw things in place and write metal nanostructures. Okay, but you can't do mechanistic chemistry under real deposition conditions. What we do is we work with Howard Fairbrother at Johns Hopkins, and we model this in a surface science tool. So Howard's a serious surface science person, and we do it under UHV conditions, where we deposit a monolayer of our precursor onto a substrate, and then Howard kills it with an electron gun, basically. And then he can do the standard surface techniques to characterize the material, and he can also do mass spec to get the fragments that are coming off the molecules. Okay. Now, why you care about being able to do this is there are already industrial applications for this. This is why we have a company giving us money to do this. One of the most lucrative applications for this is photomask repair. So the production of integrated circuits relies on photolithography, where you take a mask and then you reproduce a pattern as you go. And these masks are worth about $250,000 a set. And if there's a defect anywhere on the mask, it's totally unusable because you'll replicate the defect onto every single chip. So this is an SEM image of a defect on a lithographic mask. And so they repair these. They come in with an ion beam, cut out the area that is defective, and that's this. This is with the ion beam cut. And then you take EBID, electron beam deposition, and you write the lines back in. Okay. And then you can also do what's called circuit edit. This is for prototyping integrated circuits, where you design a circuit, you make it, and then you discover that this really ought to connect to that after the fact, so you can draw the lines back in. And then there are a bunch of cute academic things where people have made rastered patterns of dots. Here, this is a simulation of mask repair. This is an AFM tip that was constructed by EBID, and that's a magnetic wire. Now what's interesting is all these are all platinum structures, this one, and that one. And the precursors to grow platinum by EBID are terrible. So we started out here with the same set of questions. Now we have a completely new decomposition mechanism, which is electron bombardment, a little bit of thermal, but not much because you don't want to do CVD by accident. The problem is carbon content, because everybody wants to put metal structures down. They do it from organometallics, and it disasters carbon everywhere. Now we do have to deal with volatility. We need gas phase delivery, and we have to watch out about the thermal decomposition of the precursor. We need it to be stable enough not to do CVD all over everywhere. Okay, well, why not CVD precursors? And this is what the guys do who do this. These guys are all applied physicists or chemists or engineers. And so they go to the catalogs and they look for CVD precursors because they're volatile, they're commercially available. Does this sound familiar? Okay. So all of those structures that I showed you on the previous slide were made from this compound as a platinum precursor because it's volatile and commercially available. And it's a great CVD precursor for pure platinum. Does anybody who's an organometallic chemist want to predict what happens when you treat this molecule with huge electron flux? Hint, it's not that. Okay. We have a molecule here that has 5 metal carbon bonds from the CP ring. Yeah, it's a little tough to get the carbon off. Okay. EBID, this molecule gives deposits that are 20% platinum. That's what I showed you on the previous slide. Those platinum deposits are 20% platinum and 80% carbon. And these guys call this, I love this, they call it platinum contaminated with carbon. Excellent. Okay, I call that carbon contaminated with platinum. But okay. And the reason is, this is a critical part of the CVD with that compound. It's always done either under strongly oxidizing conditions with an oxygen or ozone co-reactant, in which case you're burning off the ligand to CO2, or you're hydrogenating everything off with, platinum's a good hydrogenation catalyst. Okay. So this doesn't work well. In fact, what happens on this compound is you can knock off one methyl under EBID conditions, and the rest of the methyls are all incorporated into the deposit. And so what they try to do, it's called post-deposition processing, where they basically set the deposit on fire, trying to burn the carbon out. And then you've lost your exquisite 3D control of the patterning because, well, you get it. All right, so maybe we should do better precursors. Okay, so I'm back to being an organometallic chemist. Can we salvage anything about those precursors? So if you're trying to get rid of a CP, this is old work. This is Chuck Casey and Joe O'Connor, organometallic chemists. You get rid of CP, one of the things you can do is add ligands, and you go to allyl, so you basically go A to 5, A to 3 to kappa 1. We know this is a disaster. We know that you can knock off a single bonded ligand because they're getting one methyl group off. The question is, can you still use an allyl? Because the bonding will be weaker, can you get rid of that? If you can, you open up a huge batch of organometallic chemistry. So, this was the first compound we designed. This is 3 experiments for 1. Because here's your allyl, so we're going to test the allyl, but we're also going to test carbonyls and halides to see if those things will come off under EBID conditions. Halides I could actually see, right? You could reduce them off, that'd be good. Okay, carbonyls, well, maybe, Okay, so we made a series of these compounds. These are 2 of the simple ones that we studied fairly seriously. There's a bromide and a chloride, okay? So what happens? All right, so discussed this already. Here's what happens when you do the experiment. So this is Howard's experiment, the surface science one. So it's on the substrate being irradiated. And what you can do is you can follow the oxygen in the XPS. So this is no electron flux here. Here's my carbonyls. And as you irradiate with electrons, you see the oxygen go away. Now, in this particular experiment, you can't figure out the carbon because they did it on a graphite substrate. We'll discuss that later, okay? But at least we're getting rid of the carbonyl oxygen. The bromine is still here, okay? But look at these electron doses. This is 10 to the 14th to 10 to the 17th electrons per square centimeter. If you keep beating on this with electrons, here's 10 to the 17th to 10 to the 19th, you start getting rid of the bromide. So we can knock the halide off in post-deposition processing. And then we talked them into doing a gold substrate so they could actually follow the carbon. Yeah, well, the allyl group is still there. Okay, the carbonyls are gone. But we learned something. We learned something about carbonyls, and we learned something about halides. Okay, so in stage 1, we get rid of carbonyls. In stage 2, we get rid of bromides. So let's go back to that platinum problem. Okay, the platinum problem, that platinum problem. But we know the CP is a disaster. COs work. Halides work. Let's be inorganic and organometallic chemists for a minute. So here's a very old compound that had never been looked at for EBID. Okay? And so we made this compound. It turns out to have the right physical properties. It's very volatile. It's stable enough. So far, so good. So we do the experiment. And here it is. This is the platinum dichloro-dicarbonyl. Now we're doing it on silica so that we can see the carbon come off as well. This is a better, we learn things, right? Okay. So here's the oxygen going away as we irradiate with electrons. Here's the carbon going away from the carbonyls. And the chloride, well, there it still is for the moment. We're up to the 10 to the 16th electrons per square centimeter. And it's gone by 10 to the 19th. We just got rid of the chloride too. So here's the plot of getting rid of the chloride by electron dose. Okay, there's just a little tiny bit of carbon left. So our first shot at precursor design, specifically for EBID, we went from 80% carbon in the industry standard to ours is about 10% carbon. That's not bad for a first shot. Experiments continue. Okay, so there is what happens here. We get rid of carbonyls, we get rid of chlorides, and it's all good. All right, so that's the third story. You're almost free. Okay. So I have a lot of people to thank. The people from my group are acknowledged pretty much in the slides and the names of people on the references, but here they are. These are people who've done precursor synthesis in my lab over the course of many years. On CVD, my collaborator is Tim Anderson. These are Tim's students. Robert Korotkov has a NSF Goalie project with us that I didn't talk about, but he also runs some of our TGAs. EBID, Howard Fairbrother is my primary collaborator. Utter Ingolfsson is doing gas phase electron attachment studies for this. I didn't talk about those. And I didn't talk about Evo's actual deposition experiments as well. And this is the crew for the surface plasma mediated work. These people at the bottom paid for this. I am very grateful to them for that, as to the students. And this is my group on a freezing winter's day in Gainesville. So I thank them and I thank you for your attention.
All right, so you can have some questions.
Anyone still alive out there? That was a real science class.